Hello again, back for one final lesson here. Normal approximation to the binomial. This one should be a pretty quick one, but I want to talk a little bit more about, reference in the last video about how when you find the mean and standard deviation in a binomial, you are finding mu and sigma. And same actually goes for the geometric, that you're finding mu and sigma. I want to talk about how there are scenarios where you could use um, instead of a binomial scenario, you could use it as a normal, as a z-score, and then normal CDF. We'll get into that here. Um, so we have this we have this binomial situation where x again is our random variable. We have n trials, we have a probability of p. And so then the distribution here, we've got mu of x equals np. We've got the standard deviation of x is the root of npq, or np1 minus p. Now, when we can use the normal here, the situation where we can use the normal, okay, when we can actually use a normal approximation, we need two things to be true, okay? And so the first of which is our old n times p and n times 1 minus p both have to be 10 or more. And this is simply ensuring that we have a large enough sample to be able to go from something that in a binomial is discrete, not even necessarily normal, but it's discrete, okay? And we need to be able to go from there to something where we would be able to convert that to a smooth curve. Now, again, it's not necessarily, I shouldn't even probably do it that way, since the curve might not match that because it'd be a sampling distribution. But we take something that's discrete like this here, okay? And we want to be able to convert it to something that has this density curve element to it, which would be continuous, okay? And we can use that if we have a big enough sample size, so very much like it was a condition back in the proportion unit. And then also this second one here is that we're only using less than 10% of the population. Oh, sorry, I didn't close that parenthesis. So the idea of 10n being less than capital N, we've talked about this all along. When we get into probability, we really start to see the value in it. The rationale behind 10n being less than capital N is that idea of with or without replacement. Okay, so there may be a time where we pick a value, or we pick an item out of a large bin. So let's just pretend we've got a bin of 3,400 students, and a success in this is to pick out somebody who's a senior. Okay, so we pick somebody's name out, and that person happens to be a junior. Well, now we've got 3,399 in there. We aren't putting that one back in. We've got one fail. Okay, the next one we pick out as a senior, that is a success. Okay, so these are our fails, these are our successes. So now we've got 3,398. We pick one out, and that happens to be a ninth grader. Okay, so we are counting our successes and fails here on a fixed number of trials, but we aren't replacing. Okay, these aren't going back in, and so we aren't putting them back here. Okay, and so that would normally be an issue with a binomial, except for when we're following this rule. We essentially escape it. We give ourselves a pass on it because we know that we're taking such a small portion of the 3,400 names out of this hat, and so it's okay that we aren't replacing. Okay, so it's not, it's not strictly binomial now because it does not have replacement. It's not truly independent, but we essentially give ourselves that pass as long as we're taking just a small portion. If you're asked if something's a binomial, you should still be looking for with replacement and independent. If it's asking about being converted to a normal, then you can give yourself this pass. Okay, so as an example here, it is known that 73% of our 3,430 students at MHS like the idea of having an open hour in a random sample of 100. What is the probability of that? Fewer than 60 students would like the idea of having an open hour. Okay, so in a binomial setting here, fewer than 60 would look like this. Now again, because binomial is discrete, it actually matters that we don't put less than or equal to 60. Okay, so for the normal down here, we could put less than 60, or we could put less than or equal to 60, and it wouldn't even matter. Okay, but for the discrete, it does. So this would be 100, choose 0. Okay, and the chance of a success here is the 73%. That's the parameter. And we have 0 of those up to 27, having 100 of those. plus dot 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 plus all the way up to 100, choose 60, and same sort of thing. Okay, now this all really is a binomial CDF with 100 trials, a 73% chance of success. Oh, sorry, I said 60 there. That should be 59 because it's actually less than 60. My fault, 59. So this would be 59. Okay, and so we would then go to second vars, to our distributions. We'd go to binomial CDF, and we have 100 trials. We have a 73% chance of a success. We want 59 or less successes, and that gives us a probability, you could put it on either of these now, of about 0.0017, 0.0017, or about 0.17%. So that's the chance that less than 60 students out of 100 from MHS, a random sample, would actually find the idea of having an open hour to be something that they like. So as you know, with the probability of 73, we expect to get closer, at least into the mid 60s, if not higher, in terms of how many students like the idea of having an open hour out of 100. Now, in order to make this normal, what we would do is, first of all, we got to check, is n times p and n times 1 minus p, are those both 10 or more? Well, they would be 73 and 27, so we have a big enough sample. Okay, so that's good. 2 is 10 times n, which is 1,000. Is that less than capital N here? Well, capital N in this case is 3,430. Again, capital N is population size. So we are taking less than 10% of the population. And of course, we do have a random sample here. So that would be the one last thing that we would need to make sure happens. I didn't mention that on the last slide, but that's kind of taken for granted here. So we've checked all those. Now, to solve this, now that we know it can be solved with a normal, is we would just get a z-score. So the z-score here is less than 60. So we could, in this case, because it's continuous, we don't want to put 59 here because that takes out some of what we have. So just like we did way back when with the normal, we still started at 60. Again, discrete was less than 60. This is really there's, again, in a normal curve, an infinite number of slices. So if we go down to 59, we're missing 59.00001, 59.00002. So we just go up to technically 59.999999999, and so we just say less than or equal to 60. Okay, now the mean. Well, the mean for a binomial is n times p, which in this case is 100 times 0.73. So the mean is 73. So that's 73. The standard deviation, if you recall, is the root of n times p times 1 minus p, or npq you'll see sometimes. So we've got 100 times 0.73 times 0.27. Take the square root of all that, and that's about 4.40. So that would be our standard deviation. Okay, so our z-score ends up being, let's see, negative 13 divided by that value. And that gives us about a negative 2.93. So what we're really trying to find here is what's the probability that z is less than or equal to negative 2.93. And from there we can normal CDF. CDF from negative 99 to negative 2.93. Okay, again, our curve is, here's negative 2.93, and we want everything less than that. So we normal CDF, negative 99 to negative 2.93, and that gives us approximately 0.0017, which is, of course, approximately 0.17%. That doesn't always end up being exactly the same like it did here, but in this case it worked because of our sample size and the probability that we had. So what we're seeing there is a binomial and a normal. Again, we did have to follow the rules down here in order to make this legit, But once we knew that it followed the rules, we could answer this in either way. Now, there have been not very many, but at least a couple AP exam FRQs where the rubric has allowed students to answer using either the binomial or the normal. And if you use the normal, you did have to show that it was legitimate to use it. The last thing I'll say on the normal is we could do the same thing with a geometric. Okay, a geometric just has a mu, oops, a mu of 1 over p and a standard deviation of the root of 1 minus p over p, and we would do the same thing. Okay, so we might use a geometric CDF, and maybe it's how many tries until we pick somebody that's somebody who likes the idea of an open hour. So this would be 4 or less tries. So we could do the same thing here, and we could figure out what's the probability that this is 4 or less, and use this mu and this sigma here to actually solve for z there. So so these can be used as normal much more often that we'll use them just as a typical binomial geometric, but just wanted to link that at the end. Alrighty, you've made it. Thank you, folks. Bye-bye.